Good afternoon and welcome to MAE 106 Discrete Mathematics with Probability. My name is Richard Kohar and this is lecture 17. And in today's lecture, we're going to be covering something called permutations. Previously, we did the pigeonhole principle, the sum and multiplication principle. Good afternoon, everyone. It's good to see everyone saying hello. It's almost the weekend and we'll get through this. It's not that scary, and it makes our lives a little bit easier when it comes to counting things. So there are two kinds of counting problems that we're going to be looking at in the next couple of lectures. The first one is problems where order of the objects matter, and there's and the other side of the coin, which is problems where order of the objects does not matter. So the first one that we have here, so this is kind of problems. We got two problems that we got. So that's our first one that we'll be looking at, and it's a permutation. And a permutation of a set of objects. Now, some people will go so far as to say distinct or distinguishable. Some people will go that far. It's not necessarily the case. But a permutation is of a set of objects is an arrangement of those objects into a particular order. So for instance, let's say that I have, here's some pen caps. They're wonderfully colored. They're distinguishable. And so this is called a permutation. For example, so I have some pen caps. So in this one, here is one order. I can have yellow, blue, and red. Okay, I could have yellow, red, and blue. I could have red, yellow, and blue. I can have red, blue, yellow. And the last one I can have is, well, last two is blue, red, and yellow. And lastly, blue, yellow, and red. So like this one. Okay, so there's 6 ways of organizing or putting these into an order or a permutation. So there are 6 permutations. Of these pen caps. The red, yellow, there's the Oxford comma, yellow and blue. Okay, so that's a permutation. The other one that we had up here, which was problems where the order of the objects does not matter, that is what we call a combination. So there's a permutation where that's the order matters, and the combination is where it's the number is a way of selecting objects out of a larger set where the order does not matter. And this is something that we'll discuss in the next lecture. So we can move on to our example. Like here's an example that we can start off with. How many different ways or how many different permutations of the letter A, B, and C are possible? Well, just from looking up here, we had basically 3 objects, or here's 3 letters. So we had 3 objects, and we had, from our brute force account, brute force, we know there are 6 ways, or 6 permutations. Okay. But you might be asking me, is there a faster way to do that? And the answer is yes. So what we can do is think of these, we're going to have the letters A, B, C. So you can have like, here's a word, so A, B, C would form a word, is kind of like this idea of a word. It's not a great word. It's not even a word in English, I think. So, but what we can do is we can use that multiplication principle. So what we can do is we can think of this as boxes. So in the first box, this would be the first letter of that word. So we have the first letter. And in the chat, how many choices do I have for the first letter then? Okay, so there's some people that are saying 3 and some people are saying 2. Okay, so I'll see if I can try to answer that as best as I can. The answer is 3, because on the first letter, you're going to have A, B, C. So you can pick any of those letters. Okay? Then what happens is we have a second letter that we're going to pick. Exactly, there's 3. So just kind of doing a little example below. I'll say like I have A, B, and C, and you're going to pick one. So we'll say that is A. Then that means on the second letter, we're left with how many letters to choose from? 2. So I'd be picking either B or C in this case because I picked one. So I'll cross this out and say that we'll have B down here. And then on the third letter, how many choices do we have left? Well, there's only going to be one letter remaining to choose from. So the number of choices that's going to be on the third letter is 1. So what does that equal? 3 times 2 is 6 times 1 is 6. So why is this good? I was able to quickly, using the multiplication principle, come up with that there were 6 permutations, as opposed to kind of resorting to having to list out every possible permutation. So we might not be necessarily interested in what all the permutations are. We just want to know what the total number of permutations. So that's how we can do that very quickly. So this brings me to make a general statement. So in general, How many strings of 5 digits have the property that the sum of their digits is 7? That's a very good question. But let me just get to this first. So in general, if you have n distinct objects, then the number of permutations is, so the total number is, so we start off with, we'll have, for that first choice, you'll have n. For that second choice, you'll have n minus 1. So same idea as what we're doing here. So I started out with, there's 3 objects. In the next one, there's 1 less. In the next one, there's 1 less until we get to 1. So, same idea. So this is a very powerful technique that we're using in math. We start out with a very simple problem, and we try to abstract it. And hopefully it extends. So this one would be the n minus first choice. So that would be 2 times 1, the nth choice. Now, because we encounter these products, that's what I mean by this multiplication, it's a product. We encounter these so frequent that we have a notation that denotes this. And that's what we call a factorial. And we just write it as n exclamation point. Other typographical names are also called bang. So n bang. So again, that's n times n minus 1 times n minus 2 times dot 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 all the way up to 2 times 1. That's if n is equal to not equal to 0. And for the last one is, it's 1 if n is equal to 0. And I'm also going to specify that this definition is for n in the natural numbers. So just to make sure that everyone's on the knows what I mean, the natural numbers, n, is the set of numbers 1, 2, 3, 4, dot, dot, dot. Repeat, please explain how the nth choice is 2. No, the nth choice is 1, right through there. So the n minus 1 is 2, and the nth choice is 1. This is important enough that I'll put a little box around it. There we go. So let's just do something that's a little bit simpler. Here was the question that was asked. How many strings of 5 digits? Well, let's say how many let's say 3-digit numbers exist such that the digits sum to 5. So this could go horribly wrong. I don't think I've come up with an answer for this. So, well, there's the digits that we have to work with. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now this is a little bit more difficult because we're going to have to do something what are called cases or indirect counting. So this is something that we should maybe hold off until we get to a little bit more, let's say something that's a little bit, until we've covered a little bit more material. So it's not a bad question, but it's something that we need to get back to. Okay, so we had done, here's an example. Let's say that I'm going to do 4 factorial. So I'm reading this as 4 factorial. It's not an excited 4. And we're not screaming at it. It's just 4 factorial. So what that means is we start from the number 4 and we multiply it by decreasing numbers. So what I have then is 4 times 3 times 2. So that's 12. Times 2 is 24, times 1 is still 24. Okay. So this is kind of a common one. You have, say, 4 students. You have 4 students and they're lining up for a photo. Okay, so I'll grab some markers. Here's some pen caps. So I have 4 students and their last names are yellow, green, blue, and red. And so the question is, how many ways can they line up? So let's say that we have 4 spots. And then by the multiplication principle, I'm going to be choosing one for the first spot. And then I will pick another student for the second spot and the third spot and for the fourth spot. So again, having my little 4 pen caps, if I pick one, such as that, there's 4 choices that I had initially. So starting out here, I had 4. I pick 1, and then I move on to my next choice. Now I have 3 that I'm going to pick. Let's say I pick green. And then I move on to my next choice. This is my 3rd choice. I have 2 left. I'm going to pick this red. And for the final one, I'm left with just 1. So, how many ways can 4 students line up? Well, that's 4 times 3 times 2 times 1, which is equal to 4 factorial, which we've already solved up here, which is 24. Okay. What if, so to extend this, extend this just for this class. How many ways? If there were 5 students. So just in the chat, what do you think the answer is for that one? So instead of having 1, 2, 3, 4, we're going to have one more. So we have 5. How many do you think that there's going to be? Somebody's saying 120. Somebody's saying 5 factorial. Yes, so the answer is 5 factorial. Good, because again, we're going to go 5 students. And that's equal to 120. Now, you could have done this. You could have done 5 times 4 times 3 times 2 times 1. But over here, we've already done that. We already know that this is 24. Or we also know that this is 4 factorial. Right? So we can also write that as 5 times 4 factorial. Or just if you know that you have 5 times 4 factorial and you already know what the 4 factorial is, that's 24. You just multiply the 24 by 5 to get you the 120. So that's just another little property. That n factorial is equal to n times n minus 1 factorial. And if you want to see that, it's n factorial. We do n times n minus 1 times n minus 2, n minus 3. Okay, but over here, that is by definition n minus 1 factorial. Okay. The next thing, we have 5. Moving on to page 4. How about this? We have 72 over 70 factorial. These are astronomically huge. And so, okay, you might go, okay, well, I'm not going to bother to do 72 times 71 times all that's a lot of work. There's a calculator. And we're going to go, all right, so if I'm going to, I'll done, and then there's the, where's that exclamation point? Ah, there we go, over here. We go 72, and there's a math error. So 72 factorial, just too big for the calculator. So why are we doing math by hand is because of this. We're smarter than the calculator. And to do this, we can simplify this a bit. So what I can tell you is we can kind of rewrite this so that I get 72 times 71 times 70 factorial. And it's still divided by 70 factorial. And we can cancel this out. And if everyone starts to panic, they're like, oh no, what are you doing? Blah, blah, blah. Okay, what I'm doing is 69, 68. Okay, I'm getting tired of writing that out, times 1. And over here, I have 70 times 69 times 68 times 2 times 1. So again, I can cancel this out. These are all multiplications. So I can cancel that out, cancel this out, and cancel out the 68, all the way down to the 2 and the 1. So I'm just left with the 72 times the 71. 72 times 71, 5,112. And the calculator is much happier to handle that number. So you will sometimes run into problems with calculators that can't handle it. It's simply because it overflows the memory. You can get some more expensive calculators. So you pull out a real calculator and you go 72 factorial, 72 factorial, and it gives me an answer of 6.12 times 10 to the 103, which is very large. And then I have my 70 factorial, which is 1.1 times 10 to the 100. Divide it, and I get my correct answer, 5,112. Okay. So we've kind of covered how to handle calculating a factorial, but can you explain why 0 factorial is equal to 1? Can anyone just quickly mention why we're going to use 0 factorial is equal to 1? Anything to 0 is 1? Anything multiplied by 0 is 1? Oh, well, I like to point out that if you do 3 times 0, that's equal to 0. 4 times 0 is equal to 0. 0 to the power of 1 is 1. Okay, he's mixing it up with exponents. So anything raised to a power is 1. Well, basically, we want to make sure that our definition doesn't collapse. So then if we actually made that equal to 0, if we got to the end, if we actually included that 0, so if we said 3 times 2 times 1 times 0, that would just make the whole thing 0. So there's that reason we don't include it, because we just make the whole product equal to 0. But you can also think of as 0 objects, or you can think of it as the empty set. And how many ways can you arrange nothing or the empty set? There's only one way. It's very boring, but it's just nothing. So you have nothing. How many ways can you arrange it? Nothing, but that itself is a permutation. So it's just one way. So we're thinking about it in terms of counting, like arrangements, and this is a very combinatorial way of thinking of things. Math would be so much easier if everything equals 0. Well, it would be easier, but very uninteresting then. Okay. So that was one of the questions we needed to do. Okay, so now if we go back to the example of the 4 students lining up, so we have the example here. We have 4 students lining up for a photo. And that means that we have 4 factorial, which is 24, right? That was what we had done previously. But let's say they want to have pair photos. So so there's 4 students lining up for a photo, but let's say that they want to make pair photos. So that means like a group of 2 students. So what we can say then is, for the first choice in that pair photo, there would be 4 students to choose from. And then in the second choice, there would be 3. And so that's 4 times 3, which is 12. So there's 12 ways to make a pair photo. And so we actually have a lazy way of doing this. So instead of having to write out 4 times 3, let's say twice or 3 times, can you show that with the set below? Sure. So for instance, I would have, say, let's say I have the four students right there. Good old yellow, blue, green, and red. There's 4 choices right here. And so you would pick one. So there's one choice. And we move on to the third choice. And we're left with 3. Sorry, we move on to the second choice. And we have 3 left over. So you would pick one of them right there. So there is the choice. And so because I had 4, and then on the second choice I had 3, that gives me 4 times 3, which is 12 ways. Does that help? Okay, perfect. So there is a way for us to write this out. So instead of, because we're so used to writing with factorial, you know, the long way of writing that would have been 4 times 3 times 2 times 1. And now what we have to do is we need to then cancel out by 2 times 1. And so that would cancel out that, which would give us the 4 times 3. So the way that we can do this, we actually come up with a notation for this. So what we do is we say this. We use, we're going to start out with P. So we're going to use this. This stands for permute. We have N. That's the number of objects. Then we have R. We'll say the number of choices. And we'll say that this is equal to N over, so N factorial over N minus R factorial. So if I looked over here, if I use this notation, I have P, so I'm going to permute. The number of objects or students is 4. We're going to make 2 selections, so 4 comma 2, which means that it's 4 factorial over 2. Right? Or you could think of this as 4 minus 2. And so I have 4 times 3 times 2 factorial over 2 factorial. That cancels, which leaves me with 4 times 3, which is 12. Okay, so you might have thought that was a bit ridiculous to be writing it for such a very small example. But if we ramp this up a little bit, let's say I had, let's say, 10 students. And we're going to have them in trios. Photos. So that means that they're in groups of 3. How many photos are possible? Well, then that would be 10 students in total, and we're going to pick 3 of them for each of those photos, which means that it's going to be 10 factorial over 10 minus 3 which means that that's 7 factorial. So then I have 10 times 9 times 8 over 7 factorial. That cancels out. 9 times 8 is 72, times 10 gives me 720. Okay. Okay. Now let's go back. Yeah. So here's an example. Okay, so we've done students lining up. Let's do something where it may not necessarily be students, but let's look at Steven's stocks. Steven's socks. So he's doing his laundry, but he's running out of time before he had to go on a date. So he has 3 pairs of socks. So he has 3 pairs of socks. And he didn't match them. He just threw them straight into the drawer. So there's 6 socks, and they just go into a drawer. Just in there. And they're unmatched. So how many ways can you pull out 2 unmatched socks one after another? So how many ways? Unmatched. Biggest OCD trigger. Yep, he's got let's see. There we go. There's one there, there's another one there. He's very fancy. He's got green socks, he's got blue socks. And yep, because pink was close by, he's wearing pink, or this is, I don't know, whatever it is. Wow, that's a great looking drawer. Okay, now what we could do So let's do, here's solution 1. The first way that we could do it is he picks out, for his first sock, there's 6 choices. So that's for the first sock. Okay. So he could pick any of these. He could pick a green, he could pick this purple thing, and then a blue, or a purple, and so there's 6 choices. You could pick any of those. But we want to have something that's unmatched. So for example, if he picks, let's say if he picked out, okay, so we had, here's my dots. Here's, this is great illustration. Oh yeah, that's great. So here we go. There's 6 choices there. And let's say that he picks one. Let's say he picks this one. So let's say he picked out a purple or whatever this color is. Then that means for the second sock, for it to be unmatched, it needs to be any of these then. So he's got to pick out, he can pick out a blue, 2 of the blue, or he could pick out 2 of the green. But he doesn't want to pick out that purple one, so he's left with 4. Okay. So let's say that he picked out that. What a great combination. 6 times 4, so there's 24 ways of doing that. Okay, so this is what we called the direct counting method. Direct method. Counting only the permutations we want. And here's the second solution. So we can do it the indirect method. And that is, we count all the possible ways, and then we subtract the ones we don't want. Okay. So the total number of ways of doing that would be 6 times 5. Right? Because if I had 6 socks, then I'm left over, or Stephen has then 5 socks left over, so then I'm left with, there's 30. Then we can subtract the ones that we don't want. Well, how many ways could he have done this correctly then? He could have picked any of those 6 socks, and then the second one, well, there's only one correct matching sock then. So that's 1. So I'm left with 6. So I can do 30 minus 6, which equals 24. So looking back at the 2 solutions, we see that we found the same answer using the 2 different kinds of reasoning. And because we've done that, we can feel confident in our answer. So it's good that we are matching. So sometimes you might find that one way is easier than the other. Well, that's all the time that we have for today's lecture. Thank you for tuning in on this Friday afternoon. And I hope that you check out the exercises that are posted on the website through Moodle. If you have any questions, feel free to send me an email at my RMC account. And I wish you a good weekend. We'll have to get back to those questions the next time. Okay, take care, everyone. Thank you.